Well, hey everybody, we're going to talk about electric potential today, which is going to connect our ideas of electric fields and electrostatic forces to energy and energy conservation. So if you may have noticed that we've been talking about forces, but not so much about energy. Well, that's going to change in this lecture. Um, Before we do that, I think it's important to review just the idea of potential energy from Physics 1250. So we can sort of have that on our minds and then kind of expand that definition to include how we think about potential energy in electromagnetism. So when I was in your seats taking physics in college as an undergrad, I thought that the word potential energy was just some obscure piece of jargon that didn't really make much sense. I just thought it was two words mushed together that described some mathematical thing that we did. But over time, I've realized that the term potential energy is actually a great term because it is a form of energy that can potentially be converted into some other form. So we're going to talk a lot about gravitational potential energy. So if I lift a pen, I'm increasing gravitational potential energy, but I can drop that pen and convert that gravitational potential into kinetic energy. We're going to talk a lot about that example, but there's other forms of potential energy. There's chemical potential energy and all sorts of different things. But the basic idea of it as a form of energy that can potentially be converted into some other form, the name actually makes sense. There's plenty of things in physics that I think the name is a little weird, but this one actually is pretty good. Now, you don't have to convert your gravitational potential energy into kinetic. So if you ride your bike up a mountain, you can stay up that mountain. You can live on the mountain. You don't have to come back down and convert it back into kinetic energy. The point is that potentially you could, is the basic idea of potential energy. Mathematically, we would say that if you climb a mountain or ride a bike to the top of the mountain, your potential energy has increased. So delta U. So U is your potential energy, and so you would say your final potential energy is larger than your initial potential energy. So on Earth, in a constant gravity field, this would just be your mass times gravity times the change in height. Again, delta is final minus initial, so if your final height is higher than your initial height, then your gravitational potential energy has increased. So if you're at the top of a mountain, you might say that your potential energy is increased by 1 megajoule or something like that. And then you can get that many joules back by either rolling down the mountain, falling down the mountain, parachuting down the mountain, however you want. So increases in potential energy, it's a little bit abstract, but it's not too bad, right? If the potential energy final is greater than the potential energy initial, then that's how that works. So negative potential energy, where your potential energy is decreasing, right? So delta U is potential energy final minus initial. That means the final potential energy is less than the initial potential energy. So on one level, that's a fairly straightforward way of thinking about it. Another thing to consider is that because the total energy is conserved, that means that your initial kinetic plus your initial potential equals your final kinetic plus your final potential. So we can rearrange this equation. I hope you would agree that this adds up to a constant if energy is conserved, and it is. So we can rearrange this equation and subtract things from both sides. So for example, I can subtract kinetic energy and the initial potential from this side. So make everything over here is going to be 0. And then over here, I get kinetic energy minus kinetic energy final minus kinetic energy initial, potential final minus potential initial. So I'm going to get this, and then this is the change in kinetic energy, right? Final minus initial. This is the change in potential. And so if a moment ago we were talking about how if delta U, if your potential energy is increasing, then delta U is positive. And you can think about that as your gravitational potential getting larger. But what does it mean if your potential energy is if your change in potential energy is negative? Well, all that really means is that your change in kinetic energy has to be positive, if that makes sense. So this is another important way of thinking about thinking about this topic. So there you go. I think I just said that. All right. Now, only differences of potential energy matter. So, for example, if you are climbing up a mountain and you don't go all the way to the top, but you're like mid-level, and you're just sort of walking around that mountain at the same elevation, well, then your gravitational potential is the same. So even though you're sort of walking around it, that's not actually changing your potential energy. So technically, it's really the change in potential that matters, right? Because if you started from the bottom, you're ending up at the top. The absolute number for what this is doesn't matter quite as much, right? So we could say that going from the floor here up to the second floor, there's a certain change in height. We can calculate what that is. But really, it's not so much this number, it's how much the potential energy is really changing. So we don't really have to set U at the ground level. We could set the zero potential energy at the sun or the moon or the center of the Earth or OSU Marion. If we set this at the center of the Earth, well, then the gravitational potential at the ground level at OSU Marion is going to be some large number. So exactly where you set the gravitational potential to be zero, it does not matter as much as how much your gravitational potential energy has changed, if that makes sense. So there's a thing called path independence, which is kind of like I was saying, if you're on a certain level of mountain, and you can walk around that same level of the mountain, sort of staying at the same elevation. Again, that's not going to change your potential energy just to walk around the mountain at that same level. It might not be easy to walk around the mountain at the same level, but if you were to, parachute off of it, you're going to get the same amount of energy as you would no matter what part of that mountain that you're in. So we call that path independence. And there's sort of an analogy to that in electromagnetism we'll talk about. Now, electric potential is similar in many ways. It's really the electric potential differences that matter. So the absolute value, the absolute number is there, but it really matters how much things have changed. And the main idea is that if you have two charges that are together, let's say that this one's a positive and this one's a positive, there's a certain, and you let go of them, and you let them repel and move away from each other, there's a certain amount of kinetic energy that they will get to. So in other words, that if you hold them together, it takes work to hold these things, to pull these things together. So if you pull them together from infinity, then the work that you put in is how much work that has been that is in the potential energy. It's in the repulsion between those two charges. You could also do two negative charges, that would work too. One big difference between potential energy and in the gravitational context and potential energy in the electric context is that you have positive and negative charges. Whereas with gravity, gravity sucks. Masses are positive. There is no such thing as a negative mass. There's some interesting stuff on wormholes. Like if you can make negative mass, we can make a wormhole with it, but no one can make negative mass. So again, the gravitational analogy, things are attracted to each other, they're never repelled, but that's not the case with electricity, electrostatics. So here's an analogy from the book. I forget which figure this is. But when you are accelerating a charged particle between two plates, there's a constant acceleration that's going like this, which is similar in some ways to something that's rolling down a hill. If you're rolling down a hill, there's a constant acceleration going on the hill, not so different from this case. So we are going to define something called the change in electric potential. And the spirit of this is a little bit in the same vein as the electric field. So the electric field, we created that because we didn't want to draw two maps. We didn't want to draw a map of these are the forces on the positive charges and then draw another map. These are the forces on the negative charges, and then everybody would know that one map, all the forces are pointing in the opposite direction because the charge is negative. So instead we decided to make one map, but to that map we added one rule, which is that the force on the negative charges would be the opposite direction. right? So in a similar spirit to this, we don't want to draw one map of what are the potential energies for the positive charges and another map of the potential energies for the negative charges, right? Instead, we're going to draw one map and one rule, and the thing that we're going to be drawing is going to be the change in potential energy divided by the test charge. And the test charge could be positive, the test charge could be negative, but hopefully calculating this quantity does not depend on what this test charge is. And I'll get to that, an example of that in just a minute. So if you think about what this means for the units of electric potential, this has some sort of units of joules. The charge has some units of coulombs. So the potential here has units of volts. And so what this means is that you can define a joule as a coulomb times a volt, or you can define a volt as a joule per coulomb, like we'll talk about in a minute. So let's think about this. Let's sort of break down this thing. So we have a positive charged particle at point A, and it's going to move from point B, and we're going to think about whether this increases or decreases the potential energy. And then after we think about that, we're going to say, all right, well, did it increase or decrease the electric potential? Those are two different things. So this is the change in potential energy, right? Which has a lot to do with, does it take work to make this happen, or does it just sort of, or do you let it go and then it moves just by itself? So again, we're going to think about the change in potential energy, and then we're going to basically divide it by, we're going to think about this, then divide by the test charge and see what we get for the change in electric potential. It's going to be easy because it's a positive charge here, so it's not going to be too hard. All right, so if we're going from point A to point B, the question is, has the potential energy gone up or gone down? And so if you think about it, if you think about this electric field and what's producing this electric field, well, here's a question. Do electric fields, do they go from negative to positive charges, or do they go from positive to negative charges? It's important for you to know this. So they go from positive to negative. So you can imagine that there's like a positive sheet here and a negative sheet here. So so you're going from point A to point B, and you're sort of moving away from the positive sheet and move closer to the negative sheet, kind of like that. And so a good question to ask is that if I just let go of this thing and it goes from point A to point B, will the particle actually, will it increase or decrease in velocity, for example? A related question is, did it take work? Did you have to shove it from point A to point B, push it? Or did it just sort of move there by itself? Well, for here, this particle is going to repel from this stuff and be attracted to this stuff, and so it's actually, if I let it go, it's going to increase in velocity. And so we aren't going to have to like pull it this way. If we just let it go, it'll naturally move that way, and it'll go faster in the process. And so this thing is gaining in kinetic energy, and if it's gaining in kinetic energy, well, then it's probably, yeah, that's right, then it's probably losing potential energy. This potential energy has gone down. And so at the end of the day, we find that this potential energy is negative. The potential energy has changed and it's gotten smaller. And so what we can do is we can take this and divide by the test charge and see what our change in electric potential is. And so if we do that, we start to say, okay, well, our change in electric potential is our change in potential energy divided by the charge, where the charge is positive. So if the change in potential energy is negative, a negative divided by a positive is a negative, so this is less than 0. So we would say that the change in electric potential is negative here, is what we would conclude. Delta V is less than 0. Okay? So now we can do the same thing with a negative charge. And the negative charge is going to go from point A to point B. And we're going to ask a couple of questions. And again, the things making this electric field is a bunch of positive charges over here and negative charges over here. And again, the question is, has the potential energy gone up or gone down? Well, has the velocity increased? Like if we just let it go here, would it naturally move to this spot and start moving faster? Or did we have to pull it over here to get that to work? And if you think about it, well, this negative charge is attracted to these positive charges, right? It's repelled from these negative charges, so we really would have to pull it to get it to do this. It's going to take work to get it to do that. And so, if it took work, and now it's closer to these negative charges, well, the potential is going to be increased, right? So if we had to pull on it, and now we could let go of it, it could start accelerating that way, we could get energy out of it. Well, we've clearly increased the potential energy of this situation. And now we're in a position where we can figure out what the change in electric potential is. Well, that's the change in potential energy, which the delta U is positive, but Q is negative because it's a negative charge. A positive divided by a negative is a negative at the same, and we end up with the conclusion that the change in electric potential is negative. And so this is really nice because we want to have some mathematical quantity that doesn't care about whether this is a positive or negative charge. Later on, we can go back and say, all right, well, if it was positive, how much, if it was a positive charge with this many coulombs, how much change in energy was that? But for right now, we got the same result with that the change in electric potential is negative, regardless whether it's a positive or negative charge, which again was sort of what we're going for. So, in terms of this electric potential energy, there's a nice unit that we're going to use frequently, which is that the charge of either an electron or a proton is 1.6 times 10 to the negative 19th coulombs. So if we're going to change the potential energy of this electron, change the electric potential of this electron by 1 volt, that will involve this many joules of energy. And so this many joules of energy we call 1 electron volt. And again, it's just whenever you see 1 electron volt, you should immediately see 1.6 times 10 to the negative 19 joules. This is not very many joules. But if you think about what a typical battery is, batteries are like 5 volts, USB chargers are batteries are like 1.5 volts, USB chargers are 5 volts. We're going to get you guys multimeters so you can sort of play around with some of the things at your house, measuring batteries and whatever else you feel like. Then things are usually a few volts, and so the potential energy that an electron would get in being influenced by a battery is on the order of 1 EV or a few EV. So we're going to be using this quite a lot. There's going to be questions on the exam that I'm just going to say casually, oh, this thing is going in EV. And I'll try to give you some more examples in this lecture of how to use that. Okay. We physicists often think in EV. My friends at Wright-Patterson Air Force Base often think in terms of EV. You probably haven't heard of it before, but it's a nice way to think about things. So here's a problem. So if you have 2 charged plates like we've been talking about, and let's say that we accelerate an electron from rest with 2 charged plates. By the way, this is similar to what happens at the dentist. So when you get an x-ray, you have inside of that x-ray machine, you have 2 charged plates, and you have electrons getting emitted from one of them, probably the negative plate because they have to move the other direction. And you have about 5,000 volts of potential in between the 2 of them. So if you go to the dentist and you look closely at the machine, it will say, you might say 5 kV, something like that. When you go to a proper hospital and you get x-rayed, I got x-rayed over the summer because I had a kidney stone, which is not very fun. But it was, I think it was like 20,000 volts of on this thing. Again, that's used to accelerate electrons. And so if you have 2 charged plates, and in this case it's 5,000 volts, is the change in electric potential if the electron goes all the way from one end to the other, what would be the kinetic energy of that electron in EV units? Well, it's not a trick question. It would be 5,000 electron volts, right? Because it's the change in electric potential is 5,000 volts. The charge is 1 unit of charge, E, And so you would end up with a kinetic energy that's 5,000 electron volts. And in a minute, I'll show you how to figure out what the velocity of that electron would be that's traveling with a kinetic energy of 5,000 electron volts. If you had a proton that's accelerated from rest by two charge plates have a 5,000 volt potential, what would its kinetic energy be? Well, the only difference between this case and the other case is that the proton has to be launched from the positive end instead of the negative end. Otherwise, it would just turn around, right? But if the proton went through 5,000 volts potential difference, what would its kinetic energy be? Well, so the proton has a unit charge, and so 5,000 volts times the unit charge is going to be 5,000 eV. Now, that doesn't mean that the proton is moving as fast as the electron. In a minute, I'll show you how you can calculate what the velocity this corresponds to. But what it does mean is that the proton that's traveling, whatever speed it's traveling, it's carrying the same amount of kinetic energy that the electron was. Again, this is one proton or one electron. Here's a question. If a helium nucleus now is accelerated between two charge plates, again, let's say you went on eBay, you found a dental x-ray machine, and you took some balloon helium and ionized it to get the electrons off, and then you let it through this 5,000 volt difference, what would be the kinetic energy of this helium nucleus in EV units? Well, the pattern here is that it's B, but in fact the helium nucleus is something different because the helium nucleus has two protons in it, because the atomic number for helium is 2. And so instead of being 5,000 volts, so it's still 5,000 volts difference, but the charge here is twice the elementary charge. And so the kinetic energy that this thing gets is 10,000 electron volts. That doesn't mean that it's moving any faster than the proton. Certainly doesn't mean it's moving faster than the electron. It just means that it has more kinetic energy. And I think in a minute I'll show you how to calculate what that kinetic energy is. All right, so the speed, yes. So if we have an electron that's accelerated, we want to know what the speed of this thing is. So we decided earlier that the kinetic energy is 5,000 electron volts. So I'm doing this in a little bit of a simplistic of a way. I'm saying, all right, well, we went through this much potential difference times Q. That's going to be our change in potential energy. The change in potential energy, because energy is conserved, is the same as the change in kinetic energy. But we started off with 0 kinetic energy, so this is really KE final is equal to 5,000 eV. And now that's 5,000 eV. Well, we know what an eV is, right? So 1 eV is 1.6 times 10 to the negative 19 joules. So here we're sort of converting the units in sort of the well-chosen one. So 1 eV is equal to 1.6 times 10 to the negative 19 joules. So this is technically 1. But when you multiply it by this, the units there cancel. So the eV units cancel, and you end up with 8 times 10 to the minus 16 joules, which is not a lot of energy. But then again, it's a very, very tiny particle, right? So this is the kinetic energy in joules. We can use this to figure out what the speed is. As I was saying, the initial speed is 0. And so I can solve for v sub f. So multiply both sides by 2, divide by m, take the square root, and remember that the mass of the electron is about 9.1 times 10 minus 31 kilograms, which is crazy small. And so when you do all these calculations, in spite of how small this is, the mass is even smaller, and you end up with a speed that is something like 4 times 10 to the 7th meters per second, which again is not quite the speed of light. It's still a factor of 10 or so below the speed of light. This is what you get, moving very fast, right? We do the same calculation again with the proton and do all the same sorts of things. So again, I'm being a little bit sloppy here, and I'm basically just saying that the change in potential energy is the same as the change in kinetic energy. We decided earlier that it was 5,000 eV, so it's actually the same energy in joules. Once again, the initial velocity is 0. But the proton is much heavier than the electron. And so instead of being 10 to the minus 31 down here, it's 10 to the minus 27. And so you run those numbers, you get something like this, which is still pretty fast. I mean, 10 to the 6th meters per second there is still pretty darn fast, but it's nowhere near 4 times 10 to the 7th, which is what we got on the previous slide. So again, the proton has the same kinetic energy. It's carrying the same amount of energy as an electron is, but because it's so much heavier, it doesn't need to move nearly as fast. It's kind of like saying that if you had a ping pong ball and a baseball and they had the same kinetic energy, well, that ping pong ball would have to be going crazy fast to have the same energy as, a baseball. So that's kind of what's going on here. Now for the helium nucleus, this is similar but different. So we decided that the kinetic energy is actually 10,000 eV instead of just 5,000, again because it has a charge 2 nucleus. We can convert this to the number of joules. So it's a little different now. I think this is twice as much as it was in the last problem. But the mass is even more, right? So a helium nucleus has 4 nucleons, so 2 protons, 2 neutrons, so a total of 4. Each one of those is roughly, so this is the mass. To me, the mass of the proton and the mass of the neutron are about the same, so I'm just going to say they're 4 times 1.67 times 10 minus 27, and so you can run these numbers and figure out what you get. And you end up with 6.9 times 10 to the 5th meters per second. And how did that, I can't remember what the number was from, I'm trying to remember if this was greater than or less than the proton. So 6.9 times 10 to the 5th. We got 9.8 times 10 to the 5th with the proton. So in spite of the fact that this helium nucleus has twice as much kinetic energy as the proton, it's actually moving slightly slower than the proton, if that makes sense. But still twice as much energy. Okay, so this is another formula that I'll need to explain, which is related to the example we did with the charges moving through that constant electric field. So the change in electric potential is related to how strong the electric field is. It's also related to how far you've moved along the electric field, along the field lines. And then there's a minus sign here, because as you move along the field lines, which is what we did with those positive negative charges as I was showing earlier, as you move along the field lines, whether it's a positive or negative charge, our electric potential actually decreases, which is why that negative charge is there. I have a few more things to say about this equation coming up. If you think about the units of this equation, so this is in volts, right? The electric field, as we talked about earlier, is newtons per coulomb, and then the distance along the field lines would just be meters, right? And so this is interesting because it tells us that if you divide both sides by these meter units, this is interesting because it tells us that 1 newton per coulomb is the same thing as 1 volt per meter. And so in reading quiz 3, there's a question where it asks you to convert 4 times 10 to the 3 volts per meters to newtons per coulomb. And the answer is just 4 times 10 to the 3 newtons per coulomb. So it's not intended to be a trick question, but you'll see both of these things in this course. You'll mostly see newtons per coulomb stuff in the early part of the course. For me and my friends over at Patterson Air Force Base, we almost always talk about volts per meter. And the reason for that is that if you get deep into physics, it's really the fields that are the most fundamental thing rather than the forces, which is an exceptionally long story. But in any case, my friends over at Pat really like this version, even though it's totally equivalent. Okay, another way of writing this equation is like this. Sorry, I'm out of focus here. Maybe if I stand over here. There we go. And so we still have the minus sign there. But instead of being a simple multiply, now we're treating this as a dot product, treating the electric field and the distance as dot products. And so another way to break this down, dot products you can turn into a cosine, right? Where the theta is the angle in between those two things, in between the angle of the electric field and the distance that you're traveling. And so if you're moving 90 degrees to the electric field, if you're moving 90 degrees to the electric field, you're moving, you'd be moving this way, right? Well, then you're not really changing your electric potential. It's kind of like you're walking, or over here, I don't know if you guys can see, I don't know how well you can see it, but there's these little circles here. It might be more visible in the PDF. So if you're moving perpendicular to these field lines, you'd have to move in a circle, and if you move perpendicular to them, you're going to be on this same circle. The circle is the lines of constant electric potential. And so if you're moving perpendicular to them, then your electric potential is neither increasing nor decreasing, because cosine of 90 is 0, is the basic idea. So again, these circles, the lines, are referred to as equipotential surfaces. Over here with the electric dipole, get pretty interesting. You got a positive charge here and a negative charge. Get some interesting structures there. Some people like to draw these electric potential lines as sort of mountains. So if you have a positive charge here, and that's all you've got, and you want to bring another positive charge there, so you have to work to get those two things together, right? You have to put energy into the system, and so it's kind of like climbing a mountain, essentially. Well, whereas over here, if you have electric dipole, one of these things is positive, the other thing is negative. If you wanted to bring in another positive charge next to the positive charge, it's going to take a work to get it to go closer to there. But if you want to bring a positive charge next to this negative charge, that's easy as pie, because it's attracted to the negative charge and it goes in the opposite direction. So there's some interesting surfaces there, and you can kind of see the equipotential surfaces, the lines for which the electric potential is the same. Same here, same here. I think you get the idea. You can notice, by the way, as you go further and further away, this gets closer and closer to 0. It's something you should point out. Now, we've been talking about electric field already. How does the electric field relate to all this? It turns out that the electric field is actually essentially the derivative of what you're seeing, these contours that you're seeing. And so this is a very fancy looking derivative, which we've done to impress you. But it's basically, the x component of the electric field is the derivative of the potential in the x direction. Same thing for the y direction, same thing for the z direction, and then there's a minus sign thrown in there to make sure that if you're bringing two positive things together, that the electric field is pushing them apart, essentially. That's right. Now, a question, and there is a question on the exam that is extremely similar to this, that a lot of students get wrong, which is thinking about, you're saying, okay, you have a conductor. As we talked about, the electric field inside of a conductor is 0, right? Because if there was any electric field, the electrons would immediately, very, very quickly move around to shield it until the electric field became 0, in which case things stopped moving. So if you had a charged sphere, the electric field inside of it, as long as it's conducting, would be 0, 0, 0, 0 until you got out to the edge of it, and then it would drop as 1 over r squared. That's fine. What does the potential look like in this case? What's the electric potential here? A lot of people would say that the electric potential is 0 inside of the sphere, inside of this metal sphere, because the electric field is 0. But no, that's not correct. And it's not correct for a variety of reasons. There's sort of the mathy reason why it's not correct is that the electric field is the derivative of V. And so that means that V is the integral of E, as we'll talk about. And so the integral of E gives you a constant, which is how you get the constant voltage in the middle. Another way to think about it is, and we were sort of talking about this with some of the Gauss's law problem, is that if you took this sphere and you kind of drilled into it, going down to the center, do you feel an electric field inside of it? And if you're a charged particle, you wouldn't necessarily feel an electric field, but the question is really how much energy could you get out of this thing? is what we're asking now. And so if if I had another positive charge and I brought it here and I let go, it would repel, it would go off this way, and I could calculate how much velocity it gets and figure out how much kinetic energy that it got, and I could put it even closer to the surface, and then I could let it go and see how much energy that it gets and figure out how much uh, potential energy it would have had there. And that's kind of how you make this curve, essentially, is that the closer you get to this sphere, the higher and higher the electric potential goes, which tells you what the potential energy is. But the thing is that potentially you could put a hole in this sphere and actually put the particle in there, and then sort of let it go and see how much energy you can get. And so imagine that I drill a hole in this sphere, I put the particle inside, and then I just give it I give it this little flick that involves the tiniest amount of energy, just virtually no energy involved in that little flick. But what that flick does is that starts the particle just sort of drifting, until eventually it gets out here. Then it goes up to super high energy because it was so, it starts so close here. So the point is that if you had some additional positive charged particle that you had like inside of here, and you ask, well, what is the potential energy of this particle that's inside of here that we're about to let go? Well, it's clearly non-zero, right? Because as soon as it sort of drifts out here, and it doesn't take much to get it to drift out there, then it goes up to ridiculously high energy. That's fantastically more energy than the little flick that I gave it to make sure that it would do that. And so at the end of the day, you find that the potential energy of the particle inside of this thing can't be zero. You can't say that if you had a positive charge like in the middle of this thing, that could potentially move away from it, that electric that potential energy is zero. So this has to be some non-zero value. So there's a mathy way of explaining this, but there's also just sort of like, what are we really trying to do here, and what would happen if we let go of a particle? So I'm not going to go over this, but it's a fun thing you can play around with, of putting down charges and fields and sort of getting used to what that looks like. But that's about all we have for the day. There's another electric potential lecture coming. We'll expand on these things.